Hey Internet, I hope everyone watching this is having a great day. If you have a couple minutes, I'd love to introduce you to a project of mine that I've been working on for quite a while and is finally ready to be demoed. So the project is called Polyslice. This is a 3D printing related application. So it is an AI powered slicer that's been designed specifically for the Three.js ecosystem. So I've been designing things in Three.js for 3D printing for a while. You can see some of my designs over here on Thingiverse, for instance. After designing things a couple times, I noticed I was having a bit of a problem with my workflow, and that I found it to be a very manual and disjointed process. If I wanted to print something I designed in Three.js, I'd need to first export it to an STL or an OBJ file, which would then need to be loaded into a slicing application like Cura, which would then process it into G-codes, and then those G-codes I would need to manually transfer over to my 3D printer using like a micro SD card or something like that. So not a very straightforward process. So the idea for Polyslice is that I wanted something that would allow me to go straight from Three.js mesh to a machine usable G-code, eliminating the need for intermediary file formats and third-party slicing software. So I started searching the internet for something that would do this for me. I stumbled across this Three.js issue here where people were discussing sort of a similar problem with their workflow. And I was informed that essentially the software for this doesn't currently exist, but it was kind of open for development if somebody was interested in giving it a go. So I decided to take on that project for myself, and Polyslice is the result of that. So as I said, Polyslice is designed to streamline the 3D printing workflow, but you don't need to be working in Three.js. It also has support for loading existing models like STL and OBJ models, as well as other file formats. It can process everything into machine-ready G-code, and in addition to that, it also has the ability to send the G-codes that it produces directly to your 3D printer if you're in a web browser using Web Serial API, or if you're in a Node environment using Serial Port. So this makes the entire design to print workflow a lot more seamless. It can happen in a web browser or a Node environment, and this makes 3D printing more accessible and eliminates the friction and the difficulty of moving or of using different tools. So if I still have your attention, I'd love to walk you through the installation, the quick start, maybe talk a little bit more about what exactly I mean when I say that it is AI powered, and then show you some of the stuff I've sliced already. So let's dive right in. Alright, so the installation itself is pretty straightforward. Just npm install Polyslice, or if you're working in the browser, you can use these script tags here. For quick start, this is like the very bare bones minimal code you would need to get started working with Polyslice. I'm actually going to jump over into my editor in a second and show you a slightly more detailed example, but based off of this. If you want to follow along locally, you can run these steps here, like clone the repo, navigate into the directory, install the modules, compile the code, and then run the quick start script. So let me just jump over into my editor so you can see. So obviously the first thing you'll need to do is to require all of the necessary modules. So path is required only if you're going to be loading an external file like an STL or an OBJ, or if you want to save your output G-code to a file locally as well, then path is required. Otherwise it's not needed. Three.js obviously is required all of the time. Polyslice. These are the exports provided by Polyslice. You've got your main slicer class, you've got a printer class, you've got a filament class, a loader class, and an exporter class. So that's everything that comes packaged with Polyslice. I discovered pretty quick when working on this project that the main determining factor in how you're going to configure your slicer is determined by like the printer and the filament that you're using. So to try and make your life a little bit simpler,
I prepackaged Polyslice with a few dozen of the most popular printers and filaments. So in this case here, I'm using Ender 3 and some generic PLA. So you can initialize these classes here, and this will give you a lot of the default configurations that are going to be specific to you. So that'll make things a little bit easier for you. And you can also customize these classes after initialization as well. They come with a full set of getters and setters. So I actually broke the hotbed of my printer last year by mistake. So I need to set hotbed temperature to 0, otherwise my G-codes don't run. But that's my fault, and that's something that's specific to my situation that you won't need to worry about. But just a good example of how you can customize these things post initialization. So then here's the configuration for the main slicer class. Pretty straightforward. It takes one argument that's just like an options object. You're going to want to pass in obviously the printer and the filament that we defined already, and then maybe a few other configuration options that are not specific to the printer or the filament, such as the infill pattern that you want to use, infill density, should there be a test strip, metadata, should it be verbose, etc., etc. You can check the docs for a full list of all the configuration options available, but that's a nice little sample there. And then also, like the printer and the filament, you can configure the slicer post initialization as well. For example, setting nozzle wipe to true or changing your infill pattern to hexagons. So you have that option to modify the slicer config on the fly using the setters is an option as well. So here's the actual slicing. If you're working in Three.js, this is going to be a pattern that's very familiar to you. This is just creating a Three.js mesh, a cube in this case, using a box geometry and some basic material. The only new line of code for you would be this one, which is slicer.slice, and then you pass in the mesh. So this doesn't need to be a cube. This could be anything. This could be a cylinder, a sphere, or a custom mesh. Anything, any Three.js mesh will then produce this G-code here. The other option you have as well is, if you're not working in Three.js, is to load an external file. So you can use the loader class to pass the path to the file that you want to load, and then essentially just do the same thing. G-code equals slicer.slice and pass in the mesh. So those are the two different options you have. Once you have the G-code, obviously the next thing you want to do is figure out, like, what are you going to do with that G-code. The most simple option is just to save it to a file locally. So this is an example of how you could use the exporter class with the save to file method to save your G-code to a file locally. So you pass in the G-code and the desired output path, and then you can see, for example, here my output folder is currently empty, but I'm going to run this script for you in a second here, and you'll see the output G-code will show up in here. So that's for saving for a file locally. The next, more complicated option, but more powerful option, if you can manage it, is to stream the G-code directly to your printer. So it takes a little bit more configuration and setup. You'll need to set up the serial path. This is going to differ depending on the operating system that you're using and maybe even the printer that you're using. And then there's a few other options here as well. A quick note that I had a pretty seamless, pretty smooth experience getting this to work on my Mac, but had a little bit more of a headache getting it working on my Linux laptop. I needed to modify some of the default permissions for serial ports. So anyways, just a note that depending on the computer that you're using, you might have some difficulty here, but it shouldn't be too hard. So then you just use the exporter class to connect to the serial port, stream the G-code, and then disconnect afterwards. And that's it. So let me run this file for you, or this script, so you can see. There you go. So my printer is not connected right now, so it skipped the streaming option, but it did save the G-code. So here's the G-code, the output G-code. This is created directly from this mesh, this line of code right here. That's pretty cool. That's a 3JS mesh turned directly into a G code for you. So I think that's pretty cool, and this is all you really need to get started. Although there's obviously a lot more to know. If I still got your attention even now, I'd love to dive in a little bit more into how this project was created, and like I said, show you some of the stuff I've sliced already. So let's take a look at that now. So as I said at the beginning, I'm calling this an AI-powered slicer. And what I really mean by that is that the bulk of the code, 90% or more, was not actually written by me or by any human for that matter, but was generated by GitHub's coding agent Copilot. So let's take a look at like this file, for instance, slice.coffee. This is the main entry point for the slicing algorithm. And essentially, every single line of code you're seeing here is AI generated. I didn't write a single line. I just provided the natural language prompts that instructed Copilot on what to do, and all of the code is actually, or most of the code is actually written by AI. The reason it's not 100% is that I actually started working on this project way back in 2022. Before these AI models, these language models were really popular in common use, and even at first, I didn't really start when they did launch. I didn't really start using them. It took me a while to pick up the habit. But this past year, 2025, has been very transformational for me personally as a developer in terms of learning how to use these coding tools to really increase my rate of development and the quality of the code that I write, or that I guess don't write. But yeah, it's been very, very transformational, and I can show you here actually in this is kind of like my secret weapon. If you pull up the GitHub folder here, you'll see there's a file for agents and a file for instructions, as well as if you go over to the repository pull request history, you can see all of the natural language prompts. Well, you see all the pull requests, and then you can open up any of these and see these ones have all been merged already. You can see all the natural language prompts that I used to sort of inspire Copilot to write the code. But yeah, very, very little actual human coding took place. So yeah, these prompts in the pull requests, as well as you can see here these agent files. These are agent files that I've created for performing specialized tasks. Like there's a refactoring agent for when I'm refactoring the code. There's a docs agent for when I'm writing docs. There's a test agent for writing automated tests. Like this project has 500 plus automated tests that were generated using this agent profile here. So these agents are useful for specific tasks, and then also this instructions folder. So like if you want to work on this project with me, well then that's the other big advantage I've seen with the AI. Not only has it increased my rate of development and the quality of my code, but it also really lowers the barriers to entry for people to be able to contribute and collaborate on projects. So you don't need to be a software engineer. You don't need to have a PhD in mathematics if you want to work on this project with me. You can just, as long as you can explain in English, or maybe not even in English, in any natural language, if you can just explain what is the problem you're having and how you think it should work, we can probably figure out together with the help of AI what needs to be done to fix the problem. And so if you're working on this, all you really need to do is to instruct your AI before making any coding changes to read all of the instructions in the instructions folder here, and it'll instantly know everything there is to know about the project. It'll know the tests architecture. It'll know how to write comments. It'll know the coding standards. It'll know the algorithms that we're using, the slicing algorithms that we're using. It'll know everything there is to know. So that's kind of the idea for this project going forward, that like unless you're a specialist with like previous experience working on slicers, I'm pretty much making this a no human code is kind of a rule that pretty much everything, all changes, even if it's only one line of code, everything should go through the AI. So that's what I mean when I say that the project is AI powered. Is that it has been designed with AI integration in mind from the ground up, and that 90 or even 95% of the code in this repository is AI generated, not human coded, and that number is only going to increase going forward. Like I said, unless you're a specialist, I think pretty much all coding changes are going to go through the AI through natural language prompts. So yeah, that's what I'm talking about. So yeah, now I'm going to switch back over to my browser and show you a little bit more about the steps that I went through to make this all happen. All right, so if you go over to the repository here and you click on this link here, it'll take you to this little landing page. So you can see there's two main tools that I created for working on this project. There's a G-code sender and the G-code visualizer. So neither of these tools actually, the sender here or the visualizer, actually ship as part of the package. They're just development aids. The only thing that actually ships is like the API layer of the slicer. So if you want to build your own graphical interface like on top of it, you can do that, or you can use these ones, whatever you like. So if you click on the little upload icon here, you can upload a G-code. So I'm going to go with the quick start G-code that we created earlier in the video, and there you go. There it is. That's the mesh of the cube that we sliced earlier, right out of the 3JS mesh. You can see all the different components of the G-code. This over here, this is the test strip that we turned on. So this is a little strip of filament that it lays down prior to starting the main print. This funny little line up on top here is the nozzle wipe that we turned on as well. And then this obviously is the main object. There's a couple different things you can do. For instance, if you don't want the G-code to be so like see-through, you can turn on thick lines to make the shape look a little more solid, or turn it off. Both can be useful depending on what it is you're doing. There's these vertical scroll bars over here on the left, so you can scroll through the layers from the top down, or if you like, from the bottom up. If you select an individual layer, you can use this horizontal scroll bar here to go through that layer step by step, seeing exactly how the printer is going to do it, laying down the outer walls first, and then the inner walls, and then the infill, and then moving back to the starting position for the next layer. The legend over here shows you what all the different colors mean. So like orange is outer walls, light orange is inner walls, the yellow is skin layers, that's horizontal exposure, the blue is the infill, the red is the travel lines and whatnot. And you can toggle them all like on and off. The travel lines, for instance, I usually have them toggled off unless I'm actually developing that particular feature. And you can toggle off, say you want to look at the infill structure only and study it, or you want to look at the walls only and not the infill. You can do whatever it is as you like with these checkboxes here. So as I was developing this, I started with a cube. That was the first sort of like geometry that I started with, and I didn't do all these things at once. Obviously that would have been way too much. I started with like just outer walls, so figuring out like the plane triangle intersection that was needed to create the outer walls was sort of like the first problem, and then figuring out how to inset that path to create the inner walls, that was like the next problem. And if you look in the pull request history, you can see all of these tasks sort of being accomplished one at a time. After figuring out outer and inner walls, I moved on to the skin. So again, another inset path problem here, plus figuring out how to do the zigzag lines across, and to make it only generate on specific layers. So that had again more challenges to it. After getting the skin working properly, moving on to infill was another challenge. And then I started moving on to different geometries. So after working on a cube, If you go over to actually the resources folder here, you can see G-code, infill. Let's go with like grid infill for a cylinder. Let's go with cylinder next. Give it like a 20% infill. So after a cube, I moved on to cylinders. So this had another set of challenges to it, figuring out how to clip the path so that they fit within the round shape of the cylinder only and don't extend beyond it, was another challenge. And then from a cylinder, I moved on to like a cone. This had another set of challenges, determining if the area at the top was too small to not try and generate infill here. At first it was generating infill and it was having all kinds of problems. So again, more challenges with each new geometry. The slicer was becoming like better and better. From a cone, I then moved on to like a sphere. You can see here, I've got my sphere here, and then from a sphere, I moved on to a torus. So you can see the torus here. So this was the most challenging of the basic geometries, was the torus, because of the hole in the middle, figuring out how to try and not do travel lines across the hole. So you can see the travel lines here are I'm trying not to cross the hole, and figuring out how to do the inset in the opposite direction for the hole and stuff. So again, it had new challenges. So after I was done with the torus, that was kind of the end of the basic geometries that I was slicing. But the torus got me thinking about holes and got me thinking about travel lines, crossing holes and whatnot. So I started then working on a wayfinding algorithm. So let me go here. So I developed these new shapes that are like sheets with holes punched into them. So there's like a one by one. Let me turn the travel lines on so you can see. The idea here is that the travel lines should not be crossing the holes. So there's a 1 by 1, there's a 2 by 2, there's a 3 by 3, and let me zoom in on a particular layer so you can kind of see a little bit what's happening. So you can see, like, after it's done doing the outer walls, it starts drawing the holes, and you can see those red travel lines. How they kind of, there's a wayfinding. That one there, for example, is probably the best example so far. That one right there. How it sort of dynamically finds its way around the mesh without crossing across like the hole in the center. Was quite challenging. You can see it breaks down a little bit sometimes. It's not perfect. It cuts across the corner here a little bit. But yeah, figuring out how to do that, and the same thing with the infill. When it does the infill, it doesn't cross holes at all. You can see some pretty crazy travel moves there. Figuring out how to do all of that without crossing holes was quite challenging. I'll crank it up even further. The best example is the 5 by 5. So let me pull up just one layer here, and you can see. Let me pull up a skin layer so you can see the skin as well. But you can see these travel lines here, when it has to go all the way from one side to the other. There's these large red travel lines where it's finding its way. There's like 5 or 6 different waypoints here as it finds its way across the mesh without trying not to cross any holes. So yeah, developing this again was all created through natural language prompts. I didn't write any of the code for this algorithm. This was all figured out by the AI. I was just kind of explaining to it the problems I was having, and together we figured it out. Again, when it draws the infill, the skin, it doesn't cross any holes here as well. It finds its way around the mesh without needing to. Efficiently without needing to cross any holes. So that was sort of like the next challenge that I tackled, that was inspired by the torus geometry. After that, I started working on adaptive skin problems. So like you can see in the arch example here. Now let me turn travel lines off, and infill off. And even the walls off. You can see this little skin patch here that's developed at the top of the arch, not the one at the very top. This one here. This was tricky because you have to sort of be able to detect horizontal exposure, and develop skin patches for those exposed areas. and even if it's not at the very top or the very bottom of the mesh. So figuring out adaptive skin and exposure detection like that was sort of like my next challenge. You can see it works also. If the mesh is flips sideways like this, you get these two horizontal exposure patches being detected, so that was, I started doing that with an arch, and then I moved on to a dome. So you can sort of see the same thing in the dome here. If I turn off the outer walls, you can see there's this like skin patch that's generated due to the horizontal exposure at the top of the dome. So figuring out all that was like my next challenge. And then I did also some more with pyramids as well, but just for time I won't go into all the detail on that right now. Basically, after I figured out all these sort of simple geometries and sort of isolated different challenges into these like specific sort of tests, like the holes, for example, I decided to sort of like jump into the deep end and try and slice a benchy. So if you're familiar with 3D printing, probably one of the most popular sort of designs ever, like popular all time, is this benchy design, which is sort of like a way to sort of calibrate your 3D printer just to see if everything's kind of working properly. So I decided I wanted to try and slice a benchy to see if what I'd done was working. So I took the plunge and downloaded. Well, I didn't download this file exactly. I downloaded a low polygon version of this just to sort of like start small and work my way up gradually. But you can see it here. Let me go back to the visualizer. Let me go to here. Let me go to my G-code resources, benchmarks, and my low poly benchy. So let me turn all the different components back on, infill everything. So yeah, there you have it. After slicing all those different basic geometries, I took like I said, I took the plunge and tried to do this one, which is kind of like a more interesting because it's like a real world, more complex real world object rather than just those simple geometries, which were more controlled environments. You can see there are all kinds of problems like what is this? Why is it doing that? Why am I getting these little jagged lines over here and whatnot? So I'm not really too surprised jumping from like my very controlled environment over to this sort of real world design, messy real world design, that there are some problems. And I'm going to continue working on ironing out those issues, but basically that's why I'm making this video now, is that I sliced this benchy for the first time November of this year, 2025, and decided that this was kind of like enough that I could demo the project now. It's like if I'm able to slice a benchy, it's like I have at least a minimum viable product slicer here. So yeah, I'm gonna go over now to show you a little bit more about the G-code sender, and then show you these prints for real. So let me do that. So this is the web G-code sender. I've got my printer turned on and connected now, so I should be able to hit the little green button in the corner here, select my printer from the list of available devices, and there we go, we're connected. So this is like a terminal style app. It's super useful for like learning G-code commands, sort of experimenting with them one line at a time. I can type in at the bottom here, for example, G28 is auto home. So you'll see my printer is going to give me some feedback while it's processing that command, and then should update me with its position once it's done. So there we go. We have the updated position and an OK to know that everything's OK. So there's some other commands like say G0. Let's do like X10, Y10, Z10. So this should move this is a travel move. It should move the nozzle to that location without extruding any filament. So there we go. Again, getting an OK to know that everything was fine. Or say another command here like M109 R200. This should tell the printer to heat up my nozzle to 200 degrees Celsius. So again, you're seeing some feedback from the printer while it's busy doing that. You can see the temperature values increasing here over time. Yeah, this is super useful for learning G-codes, and you also have the ability to hit the little upload button here and select a G-code, and it will stream the entire file to the printer, assuming you're connected. So for the remaining portion of the video, I think it's actually best we pop out of the computer here and into my office so you can see the printer in action. So welcome to my office. This is my little setup. I've got my 3D printer over here. This is an Ender 5 that I've had for a couple years now. So in just a second here, I'm going to double click on the Quick Start G-code, and you'll see it'll be streamed via the USB cable here to the 3D printer. So let's give that a go. So there we go. It's starting to print. The nozzle's starting to move. It's getting into position. While that's printing, I can maybe show you a couple other stuff. You can come if you want and see. These are some of the other meshes that I was showing you earlier in the visualizer, like the cube, the cylinder, the cone, the sphere, the torus, the hole sheets, the arch and dome, the pyramids, and of course the bench sheet. So this is proof that those G-codes, they didn't just look nice. They actually are machine-ready codes, and they do print for real. You can see the nozzle head on our printer here is starting to move around and print that cube from our Quick Start. And over here on the screen, you can see all of the G-code commands are being echoed back to the web G-code sender here, so you can sort of see what's going on and monitor things in real time. While that's printing, I can just talk a little bit more about sort of some of the future enhancements I'd like to see. One of my biggest problems right now is that I'm supporting only FDM slicing. The reason being that I have only an FDM printer. But I would love to support all kinds of different 3D printing techniques in the future, SLA, and even hopefully one day maybe even DMLS, which is metal printing. That's kind of like my dream, but I'd really love to get into that. So there's a long way to go, but I'm proud of how far I've got so far. Even with the help of AI, it's been an incredibly difficult challenge. What I really love about this project is how infinite it is in scope. Like, until I'm 3D printing my own airplanes, spaceships, cars, this project is not done. So there is still so much to do. It's like an endless ocean of creative energy, and I'm only just starting to tap into it. And I'm going to be working on this project probably for the rest of my life, and I'm only in my early 30s, so we've got a long way to go. And I'll be around. If you have any problems with Polyslice, don't hesitate to open up an issue or a pull request. I'll try to respond as quickly as I can. So thank you so much for watching. And I'll just show you this cube in a minute here. It should be only a couple more seconds. I'll show you the finishing part as well, so you can see the entire process from design to print. Alright, so we're on the last layer of our cube here. It should be done in only a matter of seconds here. You'll see the nozzle wipe, and the printer head should move back to the home position and sound a buzzer. So there we go. This is the cube that we designed in 3JS, sliced with Polyslice, and printed here on my Ender 5. So there you have it. That is the entire design to print workflow done with Polyslice. Thanks for watching.